Hey, this is McKinley Thompson, and this is my Lab 2 motion of a falling object. In this lab, we tracked the motion of a falling object from rest. I used a flaming hot Cheetos bag. After filming me dropping said Cheetos bag, we then analyzed the film and tracker to extract all the motion data we would need for the lab. And we used this information to create two models, one which accounted for just gravity and one which accounted for gravity and drag force. In the analysis and constructing of the models, we'll be using Newton's second law, with F net representing just gravity for one model and, like I said, gravity and drag force in the second. You can see those two equations here. When gravity is when F net is just gravity, it'll be just mg with mass and the g constant making up that equation. But when it's F grav plus the drag force, it'll be mg plus negative b times velocity squared, where obviously v is velocity and b is the drag constant. Here's my video. Short and sweet. And here's my tracker information. You can see here, this is me doing the actual point mass analysis. Here's the graph that was made in tracker, and here's the information from tracker. I have highlighted the time and y orientation because those are the two values we cared about. We didn't use x orientation in this lab. The mass of the bag was 0.015 kilograms. Y distance covered, it went from negative 5.519 e to the negative ninth to negative 1.482, and the change in time was 0.601 seconds. Our code was very similar to Lab 1, but obviously there were slight changes and we had two different models. The only discrepancy in these two models was in the model on the right. You can see we just accounted for the weight force, so just gravity, and we used this equation here. But when we made the second model, we accounted for W plus FD, which is the drag force, shown by this equation here. And this also meant we had to implement this B value, which is the drag constant. This is our gravity only model. You can see over here on the left is the model or the graph created in GlowScript, and this is the model itself. Up in the left here, or top right here, you can see the comparison of the graph we got from GlowScript and our observed graph. You can see that it's very good at the beginning, and towards the end there is some discrepancy, about 0.4. So not too much, but there is something we're missing there. When I made my second graph, I decided to include arrows which represent the magnitude of the gravity and drag force. This was done by setting an arrow to represent each force and finding a scale to properly relate these magnitudes. For my arrow scale, I ended up choosing 15, and you can see here I had an arrow to represent the weight and drag force. And for calculating B, we were told that it would have the magnitude proportional to the square of the speed of the bag and direction opposite of gravity. Direction opposite of gravity obviously means it was positive, and we got our B value to be 0.0123, and down here you can see where we implemented that in the code. Here's the actual graph and model for it. Down here you see the graph from GlowScript, and up here's the model with the orange arrow representing gravity and the blue one representing drag force. Obviously the orange arrow is bigger, which is why the bag continues to fall when you drop it. Over here you can see the comparison with green being just gravity, orange being the gravity and drag force, and purple being the actual observed thing. You can see that there was much less discrepancy when we accounted for drag force than there was when it was just gravity, though there is still a little difference there. We were able to get it much closer. Possible reasons for error: in tracker, I may not have placed the cursor exactly in the center of the bag during the point mass analysis. It was very hard to do this while the bag was moving. And then also the value for B may not have been exact. It's very possible that I did my calculations slightly wrong, or that I wasn't able to do them perfectly, and so the value wasn't exact. Terminal velocity is the velocity at which an object moving through a medium, in our case air, reaches a resistance from the medium which prevents further acceleration. If we had allowed our Cheeto bag to fall for a longer distance and longer amount of time, it would have reached the terminal velocity, but it could not in the amount of time we gave it. In our model with drag force is the one which accounts for terminal velocity, because in the one for gravity there's nothing counteracting it, but drag force shows a force interacting with gravity, kind of slowing it down. If we were to throw the bag straight downwards instead of dropping it from rest, the terminal velocity value would remain the same. It would just reach this point more quickly. Changing the initial velocity does not change the terminal velocity, just allows the object to reach it more quickly. Thank you so much for listening.